In this video, I am going to discuss about some important properties, or better to say some theorems related to connectedness. But before going through those theorems, first of all we have to remember what is the definition of connectedness and also what is the meaning of separated set. So for that purpose I have written two basic definitions initially before the results, as you can see here. So you can see in definition 1 I have written what is the meaning of separated set. Obviously you can consider any topological space x comma tau, then you can consider two non-empty subsets A and B of x, then they are said to be separated with respect to each other if we satisfies this condition. That means if A intersection B bar is equal to phi as well as A bar intersection B is equals to phi. Now we all know A bar or B bar simply represent the closure of A and B respectively. So this is the basic criteria whenever you can say two sets are separated. Now you can see in definition 2 I have discussed about the criteria of disconnected sets. Now as usual you can consider x comma tau is a topological space. Let us choose any non-empty subset of x, say that is A. Then you can say A can be termed as a disconnected structure or disconnected set if A can be expressed as the union of two non-empty separated sets. That means, for example, you can say you can write A is equals to B union C, but B and C they are separated by means of definition. So technically B and C, for B and C you must have this criteria. So I have written if A can be written in the form of B union C, then we must have B intersection C bar is equals to phi or B bar intersection C is equals to phi. These two conditions are simultaneously true. Then we can say definitely that the set A, whatever we have chosen from the topological space capital X, is nothing but a separated structure, nothing but a disconnected structure. So here you can see the pair B comma C, we can consider this one as a separation, or better to say actually this pair is considered as a disconnection of A. Now it's from this definition it is obvious, if you consider the definition of connected set, you can simply say the in a space or in a set it will be considered to be a connected structure if it is not disconnected. That means where the definition whatever we have considered earlier, if it is violated, then you can say the corresponding space or set must be connected. So whenever you want to prove any property related to connectedness, first of all you have to remember the definition of separated structure, and then you have to remember when you can say to say a set is disconnected or even it is a connected one. So without wasting any time, now let us move to some important results. These results are a little bit unorthodox, but still they are very important in terms of examination point of view. So in the first property I have described that if x comma d is a topological space, or better to say x comma tau is a topological space, you can say, because in most of the cases we use the notation x comma d for metric spaces. So better to say x comma tau is a topological space and P is a connected subset of X. And if Q is also a subset of X, satisfying this condition, P is a subset of Q which is a subset of P bar. Obviously we know that P bar represents the closure of P, then we have to show Q is also connected. Now we have the formal traditional technique, that means we can assume the method of contradiction. So let us start in this fashion. If possible, let Q is disconnected. So if it is disconnected, already I have discussed in definition 2. So by definition you can see I can consider two different sets A and B. Obviously they are separated with respect to each other, such that you can consider Q can be written in the form of A union B with the criteria A intersection B bar is equals to phi as well as A bar intersection B is equals to phi. I have mentioned this one as equation 1 and this one as equation 2. It follows from the basic definition. Now you can see it is mentioned in the question that P is a subset of Q. Actually it is a hypothesis. So Q is equal to A union B. So from here we can say P must be a subset of A union B. That means P is contained in the union of two different separated sets A and B. Now by means of a standard result we can say in this situation we have either P is a subset of A or P is a subset of B. I must consider, you must have heard about this result where you can write this one. These are another important theorem I must say here. So if P is a subset of A, then technically you can say closure of P must be a subset of closure of A, because we also know actually in terms of closure it will maintain the same criteria. So let us take intersection with B on either side. So P bar intersection B should be a subset of what? A bar intersection B, and hence you can say because A bar intersection B from equation 2 this is equal to phi, so technically you can say P bar intersection B is a subset of phi. But at the same time we also know null set is a subset of every set, so consequently phi is also a subset of P bar intersection B. So by virtue of 3 and 4 we can say only possibility here is that P bar intersection B should be equal to phi. So we have obtained equation number 5. Now already we have explained Q is equals to A union B. Remember initially we have assumed this one. So Q is also a subset of P bar because it is in the given hypothesis. If you can't remember, then let me show you again. It is mentioned in the question, P is a subset of Q, Q is also a subset of P bar. Okay, so here you can see I have written the same thing, Q is a subset of P bar. Now because Q is equal to A union B, that means A and B both of them are smaller than Q. So B is a subset of Q which is further contained in P bar. So if I want to take the intersection of P bar and B, definitely the outcome should be B because B is the smaller one in comparison to P bar. So this is equation number 6. So already we have obtained P bar intersection B, that is equal to phi, because in the previous equation I have shown this one, P bar intersection B is equal to phi, that is in equation number 5. Now I can show that P bar intersection B is equal to B. So just combine these two results, you can say from 5 and 6 we will get B is equals to phi. But practically again this is not possible at all because we know A, B and A must be non-empty. So I can write this is a contradiction, and hence you can say why this type of contradiction arises in this situation, because you have assumed Q is disconnected, which is not possible as we have proved here. So Q must be a connected structure. So you can see the proof is complete in this fashion. So this is an important result. This is an important result. You can go through this proof and you can prepare this one for your examination. Now moving on to another important example, the closure of connected set is connected. This is again a very important result. So actually you can prove it with the help of the previous theorem also. That's why I have given an independent proof, and also I have mentioned in a note that if we consider the previous result, then we can take the help of it to prove this one. For example, we can start in this fashion: y is any subset of x comma tau, then definitely every set is a subset of itself. So y is a subset of y, which is further contained in what? Y bar. Just remember the sequential structure. You can consider this relation again. P is a subset of Q, which is a subset of what? P bar. Then Q is connected. In the previous theorem we have proved this one. So here you can see P and Q both are identical to y, and consequently you can say, so if y is connected, then y bar is also connected. But because this theorem is extremely important, better to consider an independent proof. Now let us check the independent proof. It is very much similar to the previous one. So again we can take the help of method of contradiction. If possible, y bar is disconnected. So as usual, by definition we can say we can find out two non-empty sets A and B satisfying the criteria y bar is equals to A union B, because these are separated structures. So A bar intersection B should be phi, A intersection B bar is also equal to phi. Because of the definition of closure, we know y must be a subset of y bar. Because y bar is equals to A union B, so y must be a subset of A union B. Again, by means of a standard result, you can say whenever there exists a connected set which is contained in the union of two different separated sets, as you can see in this case, one is A, another one is B. So either you must have y is a subset of A, otherwise y must be a subset of B. Now let us choose any one simple instance. If y is a subset of A, then what will happen? Simply you can write y bar is a subset of A bar. Now I hope you can find out similarity with the previous proof. I have also adapted the same technique while proving the previous result. So y bar is a subset of A bar. Just take intersection with B on either side. Then A bar intersection B is equal to phi. So y bar intersection B is also equal to phi. Because null set is a subset of everything, so phi is also contained in y bar intersection B. So just combine these two, then you will get y bar intersection B should be equal to phi. This is the equation 1. But y bar is equals to what? A union B. So definitely B is the smaller portion. So B is a subset of y bar, and hence if you take the intersection of y bar along with B, it should be B. So this is the equation number 2. So combining these two, we will get b is equal to 5. But again you are getting a contradictory idea because b can never be non-empty. So our assumption is wrong, and hence the main criteria which is responsible for this false assumption, that what was that? Initially you have assumed if possible y bar is disconnected. So this is not acceptable, and hence you can say y bar must be connected. So closure of any connected set is connected, and that's the proof of this theorem. Now I have shown another important example. As you can see here, I have given this question: show that every line segment in R2 is connected. I am not saying that real number system is connected. That is another theorem, that has an independent proof. But actually you can consider this one as a problem, that every line segment is in R2 is connected. So as you can see, I have considered a certain line segment PQ drawn along x-axis. So let us start with the same criteria. PQ be a line segment in R2, and we are considering P as origin, as you can see this one. So we can simply produce PQ as the axis of x, as I have mentioned earlier. Consider this one in the direction of x-axis and simply consider a perpendicular with respect to P. As you can see, this perpendicular line, this portion, or better to say line, whatever you say, that must be perpendicular to Px, and hence you can consider, as Px is nothing but equivalent to x-axis, so Py will be what? Y-axis. Now we are choosing any point Q over this line segment Px. So this Q must attain the coordinate of the form x, 0, because hypothetically it is right now lying on x-axis. We can also define a mapping in this form. F maps from 0, x. You can see 0 is closed because you can consider origin, but x is arbitrary to R2. So whenever you are considering any functional structure, the outcome is considered in the form of some ordered pair. Obviously by construction you can easily understand this is continuous. Now imagine there exists suitable point x0 belonging to this interval 0, x. Obviously this is semi-open or semi-closed, whatever you can say. Now you can select different points. Assume that x1, x2, x3, in this way you are considering different points, so that you can create a sequence that may converge to the point x0. That means hypothetically fx is equals to x, 0. So fxn can be considered as xn, 0. Just consider this structure. But if, as per your assumption, this sequence xn is converging to x0, then this part will also converging towards x0, 0. So by sequential definition we can say fxn is also converging towards fx0, or in simple words you can say f is continuous at the point x0, whatever we have taken from this interval. But arbitrarily x0 has been selected. That means you can say f must be continuous throughout the interval 0, x. Now we have that standard result. As I have mentioned here, every interval on the real line must be connected, and because 0, x, this is no such exception, so it is also connected. And so you can say if f is connected, and we also know that if you want to consider the continuous image of a connected set, that is also a connected structure, so you can say f image of this interval is also behaving like a connected subset of R2. So finally we can say, if you consider 0 to x as p, q, that means this is the line segment and this is the f image as per our construction, so pq must be connected. But the problem is that here you have taken PQ in an arbitrary fashion, so that means PQ is an arbitrary line segment. That means each and every possible line segment belonging to R2 must be connected, and that's why we can say the proof is complete. So this is an important example. You can also prepare this one for your examination. Now in a similar fashion, I have given one particular problem, so that you can try this one to figure it out. If you have any doubt, you can ask me in the comment box or in the comment section, better to say. Said every circle is a connected subset of R2. Here you can take the help of polar coordinate system to prove this problem. So I hope you will find this video beneficial for you, and thank you.